Welcome back, everybody. Learning as a hobby here. Um, I want to finish up section 1.5 in the Simmons book today. So we're going to do the exercises for section 1.5 in this video. Before I get to that, though, I just want to make a little bit of, tell you a little bit what is coming up soon this week on the channel. I know I said I wanted to finish up chapter 1 in Simmons and chapter 1 in Schifrin, but I have had a few comments on the videos from I guess fans of the Spivak book who want me to continue with that. So I think what I will do, just to appease those guys, because they've been waiting nice and patiently. So I think what I'll do is after I do this video on Simmons, I'm going to spend the rest of my time this week trying to finish up chapter 4 in Spivak, just to get that out of the way, and then we'll continue finishing up chapter 1 here and chapter 1 in Schifrin, and then we'll continue going back around in the usual way. So if you're a fan of Spivak, look out for that. I'll be, like I said, I'll be putting all my attention into finishing up chapter 4 and then in Spivak this week. The other thing is I want to finish up also my 3-video sequence on my algebra books. So I'm going to try and, after this video, I think I'm going to try and maybe record the video for that. Remember I said I was going to do it in 3 parts, the video for my algebra books. The first one was linear algebra, my linear algebra books, then my abstract algebra books, and then the last video will be sort of like all the other extraneous algebra stuff that I have, like Galois theory and so on. So maybe I'll record that video after, well, I'll probably have some lunch and then I'll record that video afterward in the afternoon. So yeah, so that's what you have to look forward to this week. Spivak and the finishing of the 3-video sequence on my algebra books. All right, so but anyway, that's neither here nor there. Let's let's finish up section 1.5 in Simmons, which let me just bring up my solutions here. Okay, so there are 13 problems in the exercise set for this section, and I did all of them except for one of them. I kind of wanted to do all of them, but I wanted to get this video out today, and I didn't want to wait any longer. So there's one problem that I didn't get around to, which was number 12. So I'll show you when we get to it. But all the other problems I did. And just a disclaimer also here. I say this periodically, but it should be it's good to repeat it over and over again. If you're following along with these videos, you should try the problems first before looking at my solution. You'll get more out of the problems that way, rather than just passively looking at the way that I solve the problem. It helps to think through it and struggle with the problem yourself, and solve it yourself before you look at someone else's answer. So just a heads up about that. Make sure that if you're following along with these videos, make sure that you're trying the problems before looking at my solutions. All right, so here's question number 1. If the air resistance acting on a falling body of mass m exerts a retarding force proportional to the square of the velocity, then dv dt is g minus cv squared, where c equals k over m. If v equals 0 when t equals 0, find v as a function of t. And they want us to find what the terminal velocity is in this case. So here, this is the case of when air resistance is proportional to the square of velocity. In the section itself, we did an example where air resistance was proportional to just the velocity itself. So here, this is a slightly different model that we're going to get. So here's the differential equation, dv dt equals g minus cv squared. This is a relatively easy differential equation to solve. As usual in chapter 1, all these are going to be separable differential equations. So separate variables. Now, the only difficult part here to this integral is that in order to do the integral on the left, you have to use partial fraction decomposition, which is what I'm doing over here. Right. So when you go through the partial fraction decomposition, you get this antiderivative on the left-hand side, and on the right-hand side, you get t plus your arbitrary constant c1. I'm calling it c1 just to distinguish it from the parameter c over here. All right, and then just solving for v, going through the algebra here, and plugging in, your initial values to figure out what the constant c squiggle is over here. When you solve for v, you get and plug in the values to get the value of c squiggle, then you get this function here. So square root g over c times 1 minus e to the negative 2 square root gc times t, divided by 1 plus e to the negative 2 square root gc times t. And then finally, so that's the velocity at time t. And then they asked us what the terminal velocity was. So you just take the limit of v as t goes to infinity. So those exponentials go to 0 when t goes to infinity. So the terminal velocity is the square root of g over c. All right. That's the answer for part 1. Question number 2, a torpedo is traveling at a speed of 60 miles per hour. At the moment it runs out of fuel. If the water resists its motion with a force proportional to the speed, and he says, see the footnote in the book, which I'll look at in a second. And if 1 mile of travel reduces its speed to 30 miles per hour, how far will it coast? So the footnote in the book just talks about generally we make a there's a difference between speed and velocity, because speed is a scalar quantity and velocity is a vector quantity. But here in the footnote, he says, in the treatment of dynamical problems by means of vectors, the word velocity and speed are sharply distinguished from one another. However, in the relatively simple situations we consider, it is permissible and customary to use them more or less interchangeably, as we do in everyday speech. So here he's using speed and velocity interchangeably in this particular problem. So just a note. Okay, so solution dv dt equals negative kv. That's the differential equation that governs the motion. Solve that using separation of variables. You get v is equal to 60 e to the negative kt, and then integrate one more time to get the position. So the position in terms of t is equal to 60 over k times 1 minus e to the negative kt. When you solve for everything. We still have to figure out what the value of k is, and to do that we use the other values that they gave us. They said that the velocity was 30 meters per second after the torpedoes traveled 1 mile. So plugging that in for the equation for x and solving for k allows us to do that. Here, if you could solve for t star here, which is the time that it takes for the torpedo to travel the 1 mile. Plug that into v and you can solve for k. So when you simplify everything, you end up with the equation 60 minus k equals 30, and then solve for k, which gives you that k is 30, and then that gives you the model. So this is the model here. X is 2 times 1 minus e to the negative 30t. And then you can figure out how far it coasts by taking the limit as t goes to infinity of x, and it travels 2 miles. It coasts for 2 miles. All right, question number 3 is basically like a pre-calculus problem. So I'll go through it relatively quickly because hopefully you guys know how to solve problems like this already. Question 3 says, a rock is thrown upward from the surface of the earth with initial velocity 128 feet per second. Neglecting air resistance and assuming that the only force acting on the rock is a constant gravitational force, find the maximum height it reaches. When does it reach this height, and when does it hit the ground? Answer these questions if the initial velocity is v0. So like I said, this is basically just a pre-calculus problem. You get the position is quadratic. It's equal to negative 16 t squared plus v0t. And then, to find the maximum height, you find the vertex, which is in this particular case is 4 seconds, right? Use negative b over 2a to find the value of t, and then plug that in for plug that value of t into the position function, and that tells you what the max height is. And in this case, you get that the max height is 256 feet. And here, if you look in terms of v0 and the acceleration due to gravity at the surface of the earth, you get that the max height is v0 squared over 2 times g. But here we have the actual value for g. We're doing it in feet per second, I think. So 2 times g would be 64. So that's the value of the max height in terms of v0. Okay, and then finally it hits the ground when S is 0. So solve for T in those cases, and you find that it hits the ground after 8 seconds. Right. So like I said, I won't belabor that one too much because that's basically, like a pre-calculus problem. 4, question 4, a mass M is thrown upward from the surface of the Earth with initial velocity v0. If air resistance is assumed to be proportional to velocity with constant of proportionality k, and if the only other force acting on the mass is a constant gravitational force, show that the maximum height attained is this given by this expression here, and use L'Hopital's rule to show that this quantity approaches v0 squared over 2g in accordance with the result of problem 3. In other words, show that when you can if you neglect air resistance, then the max height here simplifies to the max height in the previous case, right? The simpler case, right? So here, this is our differential equation. M dv dt equals negative mg minus kv. That's from Newton's second law. And you can divide out by m, which gives you dv dt is negative g plus kv over m. Now here in this, actually in this problem, the max height that he has here being positive, being in having the sign convention that he has here, I think what he did was he actually set this equal to a positive g plus k over mv, whereas I chose the downward direction to be negative. I guess he chose it to be positive, but it's just a sign convention, so depends on how you choose your axes. To me, it makes more sense to choose down to be the negative direction. So I get a slightly different answer than he does. It's basically the same answer, but up to a sign. So let's just go through the problem here. So solving the differential equation, we get this antiderivative on the left-hand side and on the right-hand side. And then we can solve for C squiggle by plugging in the initial values. So at time 0, V is V0. So that gives us that C, the arbitrary constant, is G plus K over M V0. Plugging that in, we get our velocity equation over here. And then integrate this one more time to get the position function, which I have over here, and then plug in your initial values to find your arbitrary constant. So here it's the projectile starting at a height of 0 at time 0. So C0 ends up being this expression over here. And plugging that in, we have our velocity equation here and our position equation here. Right, and then to find the max height, that's when v is 0. So set dy dt equal to 0, and we don't know what time that happens at. So I'm just calling it t star, and you can solve for t star here, and plug it into the position function, and that gives you this expression. And like I said, if you notice, this is the expression that he has above, but just the negative of it. And I think that again, that's just because of the sign convention I chose as opposed to his. So our sign conventions were opposite to each other. But you can see it's the same quantity, just the negative of it. Okay, so and then lastly, they wanted us to show what happens in the case where you can ignore the air resistance. Sorry, I can't remember the term. Where you can ignore the air resistance. So that's when k goes to 0. And in order to take that limit, you actually have to use L'Hopital's rule, which I'm doing over here. And when you do that, you can see that everything simplifies to give you v0 squared over 2g, which is the quantity that we had in the simpler case in the previous problem. All right. Okay, question number 5. The force that gravity exerts on a body of mass m at the surface of the Earth is mg. In space, however, Newton's law of gravitation asserts that this force varies inversely as the square of the distance to the Earth's center. If a projectile fired upward from the surface is to keep traveling indefinitely, and if air resistance is to be neglected, show that its initial velocity must be at least square root 2gr, where r is the radius of the Earth, which is about 4,000 miles. And if you plug in the numbers, when you solve the problem, you'll see that this is approximately 7 miles per second or 25,000 miles per hour. And he does give a hint here on how to set up the differential equation. If x is the distance from the center of the Earth to the projectile and v is dx dt is its velocity, then you can use the chain rule to write the second derivative of x with respect to time as v times dv dx. All right. So using that hint, here we have just by Newton's second law, m times dx squared the second derivative, right, of x with respect to time is negative g capital M over x squared. Now here, I don't, if you're not familiar with Newton's law of gravitation, g is called the gravitational constant, and capital M is the mass of the Earth, whereas little m is the mass of the projectile. So here I'm using Newton's law of gravitation. I think he says to do that here, right? Use Newton's law of gravitation. Yeah. So that's what Newton's law of gravitation tells you. And then using the hint, we get the differential equation v equals dv dx equals negative gm over x squared. And then we can solve that differential equation by integrating. Here I'm using limits of integration just to make solving everything a little bit quicker. So the initial velocity is v0, and then the velocity of time t is v. So you integrate b d beta, just so I'm using a dummy variable here, over the interval from v0 to v, and that gives you 1/2 v squared minus 1/2 v0 squared, which is the difference in kinetic energy, I guess. And then on the other side, you have the integral negative gm times the integral from r to r plus x. The r, remember, r is the surface of the Earth, so the projectile's traveling from the surface of the Earth up to a height of x above the the surface of the Earth. So r from r to r plus x, right? And again, here I'm using a dummy variable, so integrate the gamma over gamma squared, which gives you the integral gm over r plus x minus gm over r, and then just solving for v squared here gives us this expression. And then using the fact that at the surface of the Earth, the acceleration due to gravity is approximately constant. It's approximately, we call it the letter g, but it's approximately 9.8 meters per second squared, or there's another value for in feet per second or whatever. But anyway, I'm just calling it g here. Divide by m, and you get that gm is equal to gr squared. So divide by m, multiply by r squared, and you get that that's true. So I plug that in for gm, just so I have all the variables that I know something about here in the formula. So you get v squared is 2gr squared over r plus x plus v0 squared minus 2gr, right? And now notice that v squared is always positive, right? Is always never zero. V squared is never zero if under the condition that v0 squared minus 2gr is less than v squared. I'm sorry, sorry, let me say this again. V0 squared is greater than V0 squared minus 2gr from the formula. V0 squared is positive when V0 squared minus 2gr is positive, right? Is greater than 0, which gives us that V0 squared has to be greater than 2gr. Take the square root of both sides. Taking the square root preserves the order relation. So as long as it's the positive square root, v0 is greater than the square root of 2gr, which is the escape velocity. All right. Question number 6 is related to question number 5. In problem 5, if VE denotes the escape velocity and V0 is less than VE, so that the projectile rises high but does not escape, show that H equals V0 over VE squared, divided by 1 minus v0 over ve squared times the radius of the Earth, r, is the height it attends before falling back to the Earth. Sorry, before falling, it falls back to the Earth. Okay, so here's the solution. This is what our solution for v squared looked like from question number 5. This projectile reaches its max height when the velocity is 0. So set v squared equal to 0 and solve for h. When you do that, you end up with the expression that they wanted us to have. So it's just basically algebra. So this is what you end up with. All right. Question number 7, apply the ideas in problem 5. Oh, let me just adjust my leg here. Apply the ideas in problem 5 to find the velocity attained by a body falling freely from rest at an initial altitude 3r above the surface of the Earth down to the surface. What will be the velocity at the surface if the body falls from an infinite height? So here, using symmetry, the velocity, that changes in the same way going up as it does going down. So if I know what the initial velocity was, the velocity that the projectile hits the ground with will just be the negative of that. So using that fact, I can use the formula from question number 6 to do this. So set h equal to 3r and solve for v0. And again, this is just basically an algebra problem. Then you get v0 is plus or minus the square root of 3gk over 2. Therefore, the body will be traveling at a speed of magnitude square root 3gr over 2 when it hits the ground. If it starts at an infinite height, same thing holds, so it'll hit with the escape velocity, okay, 2g, which is square root 2gr. Oh, that's the end of this Jamboard, so let me go to the next one. So question number 8 says, inside the Earth, the force of gravity is proportional to the distance from the center. If a hole is drilled through the Earth from pole to pole and a rock is dropped into the hole, with what velocity will it reach the center? Right. So again, I'm just using that formula from question number 6. Right. So here, if the max height is r, meaning it starts at the surface of the Earth and it's going down, then you solve for v0 to figure out what the velocity would be when it hits the center of the Earth, which would be plus or minus VE over square root 2, but it'll actually be negative because it's going down, right? So it'll hit, when you simplify this, you get plus or minus square root G over R. So because we're considering down the negative direction, it hits with velocity negative square root G over R, right? Again, that's just using that formula and algebra to solve. All right, question number 2 has how many parts to this? 2 parts. Yeah, 2 parts. So part A says, show that the length of the part of the ellipse x squared over a squared plus y squared over b squared equals 1. And here we're assuming a is greater than b, meaning that the semi-major axis lies horizontally and the semi-minor axis is vertical. That lies in the first quadrant is given by that integral, where e is the eccentricity, and then part B asks us to use the change of variable x equals a sine phi to transform the integral into in a into this form here. In other words, they want us to write it as an elliptic integral of the second type. All right, and that'll give you the length of the entire ellipse by just multiplying by 4. So meaning that the length of the ellipse will have this value 4a times the value of the elliptic integral, evaluated at e comma pi over 2, right? So let's do part A first. This is just a calculus 2 problem. You just find the arc length integral. So find your arc length element, which is the square root of 1 minus 1 plus dy dx squared square root times dx. So that's what I'm doing here. And when you simplify everything, you get the expression here. This quantity b squared over a squared minus 1 is the negative of the eccentricity of the ellipse. So that's where the negative sign comes from over here. I'm sorry, the square of the negative of the square of the eccentricity, right? So you get this expression. Therefore, you plug it into the integral and you get what they wanted you to show in part A, right? For quadrant 1, your x goes from 0 to a, right? You're integrating over the rightmost half of the semi-major axis of the ellipse. Right, and then part B, make the substitution that they asked us to make. If x is a sine phi, then dx is a cosine phi d phi, and if x goes from 0 to a, then phi goes from 0 to pi over 2. Right. If you're integrating over quadrant 1, the angles go from 0 to pi over 2, right, whereas x goes from 0 to a, which is the center of the ellipse to the larger vertex, horizontal vertex on the ellipse. Okay, so we get, when we plug in the substitution, we get this integral here. So the integral from 0 to pi over 2, a squared minus a squared e squared sine squared phi divided by a squared minus a squared sine squared phi. You can factor out the a squareds and cancel them. And then, don't forget to multiply by the differential a cosine phi d phi, right? And in the bottom, notice that you get when you cancel the a squares, you get 1 minus, well, if you distribute the square root, you get square root of 1 minus sine squared, which is the square root of cosine squared, which is cosine squared in quadrant 1. And then you can cancel the cosine phi in the numerator with the cosine phi in the denominator. So the integral simplifies um, to a integral 0 pi over 2 square root 1 minus e squared sine squared phi d phi, which is a times an elliptic integral of the second type, evaluated at e and pi over 2. All right. Question number 10, all the rest of these are very similar problems. They just want you to write things in terms of elliptic integrals. So show that the length of one arch of y equals sine x is 2 root 2 e. About e is the notation there. If you're not familiar, e stands for the elliptic integral of type 2, and the input values are, in this case, square root 1 over 2 comma pi over 2. So let's just do that. So to find the length of the arch, again, use the arc length formula from Calc 2, and you get that the arc length integral, where is it? Looks like this when you plug everything in. And then I can write cosine squared x as 1 minus sine squared x. So you get the integral here. Actually, once I can, the graph of one arch of the sine function, it's symmetric, right? So you can actually go from 0 to pi over 2, and then you'll get the whole thing by just multiplying the integral by 2. So that's what I'm doing over here. So you get 2, that's equal to 2 times the integral from 0 to pi over 2, square root 2 minus sine squared x dx. And then you can, oh, actually, this should be phi, right? Did you say make the substitute, or did it? I guess I just used x. I didn't use phi, whatever. It's the same thing. 2 minus sine squared x dx equals, and then you can factor out that square root of 2 from inside the integral. So bring that out in front, you get 2 radical 2, integral 0 pi over 2 times square root 1 minus 1/2 sine squared x dx, which is exactly what we wanted. That's the same thing as 2 radical 2 times the elliptic integral of the second type, evaluated at 1 over radical 2 comma pi over 2. So that's what they wanted us to do. Same thing over here for question number 11. Show that the total length of the lemniscate r squared equals a squared cosine 2 theta is 4a times the elliptic integral of the first type, evaluated at square root 2 comma pi over 4. So again, same thing, use the arc length formula. Here, the only difference here is that the arc length formula has to be in polar coordinates because we have a function written in polar coordinates. So the arc length integral here ends up being integral 0 to pi square root a squared cosine 2 theta plus a to the 4 sine squared 2 theta over r squared. And simplifying everything, we end up with this integral here, 4a integral 0 to pi over 4 d theta over root cosine 2 theta. Okay, and I can write cosine 2 theta using a trig identity, the what is it, the half angle identity, or not the half angle identity, it's this one. I forget what the name of it is. Let me just write it down so that people know what I'm talking about here. So I'm using the identity cosine squared 2 theta is equal to 1 minus 2 sine squared theta. Right. There's actually a number of half angle identities for cosine cosine squared, but this is one of them. So this is the one that I'm using. And when you do that, you get this integral here, and this is an elliptic integral of the first type. Here, the first value for the input is the square root of this number, so square root 2, and the upper limit here is pi over 4. So that's what they wanted us to do. All right, let me just clean this up. Okay, moving on. Question 12. Oh, this is the one that I skipped. Just because all these problems are very similar. They're just they're like Calc 2 problems, but they just want you to write the integral um, in terms of elliptic integrals. So here, that's what they want you to do. They want you to find the surface area of the cylinder that lies inside the sphere. There's a sphere in it. Well, whatever. I'm not going to read it out because I didn't do it. So they're just Calc 2 problems, and they want you to write the integrals that you get in terms of elliptic integrals. But I didn't do that for, like I said, I just wanted to get this video up today, so I skipped that one. Question 13 is, again, very similar. They just want you to write an integral in terms of elliptic integrals. So I'll end with this question here. There's actually 3 integrals that they want you to do it for. 13 says, establish the following evaluations of definite integrals in terms of elliptic integrals. So here they want us to do it in part A for the integral from 0 to pi over 2 dx over square root sine x. They want us to show that that's equal to square root 2 times an elliptic integral of the first type, evaluated at 1 over radical 2 comma pi over 2. And they give us a hint here. It says put x equals pi over 2 minus y. And then let cosine y equal cosine squared phi. So actually, let's do that one first, then we'll do the other. We'll do them one at a time. So here's the solution for part A. All right, so this is the integral that they want, and I'm just using the hints that they gave us. Let x equal pi over 2 minus y, then dx is equal to negative dy. So you get this integral when you make the substitution. The integral from 0 to pi over 2, 1 over square root cosine y dy. Okay, then make the second substitution that they said, let cosine y equal cosine squared phi. And if you take the differential of both sides for that substitution, you get negative sine y dy equals negative 2 cosine phi sine phi d phi. And then you want to write dy in terms of phi. So, using this expression that I have down here, cosine squared y by the substitution is equal to cosine 4 to the 4th power of phi. And that means that sine squared of y is 1 minus cosine to the 4th power of phi. And just plugging that in over here and solving for dy, you get this differential that I have written here. Oh, and also, actually, there's one other step that I didn't write down, but you can factor this as the difference of 2 squares. And 1 minus cosine squared phi is equal to sorry, hang on. What 1 minus cosine squared. Oh, that's equal to 1 minus cosine squared phi is sine squared phi, and then you take the square root, which gives you sine theta, and that's why I canceled the sine theta here. So you get this expression when you simplify everything. So because I skipped over writing some of the steps here, you might want to actually write that out yourself, just to make sure you know where all the pieces came from, and then plugging that into that substitution into the integral. The bounds don't change because you can see that by plugging in the bounds for y, you'll see that phi, the values for phi are the exact same values. So the integral becomes integral 0 to pi over 2 cosine phi times square root cosine squared phi times square root of 1 plus cosine squared phi. The square root of cosine squared phi is just cosine phi, or actually it's the absolute value of cosine phi, but cosine's positive over the first quadrant, which is the same range that we're integrating over, so you can cancel the cosine phis, and you're left with, I brought the 2 out in front as well, so you're left with the integrand 1 over square root 2 minus sine squared phi, and you can factor out the square root of 2 from the bottom. 2 over square root 2 simplifies to radical 2, and there's your elliptic integral, so you get what you want. Right, so part B, again, very similar problem. They're giving you an integral. They want you to write it in terms of elliptic integrals, and they give us a hint here as well. Let cosine x equal cosine squared phi. So let's do that one next. Right, so here's the integral that they wanted us to rewrite. And I'm just using their hint, let cosine x equal cosine squared phi, find your differential, yada yada, similar type of thing that we got from the previous problem. So this is your differential, plug it into the integral, you get this expression here. And cosine squared phi is the same thing as 1 minus sine squared phi, which I can rewrite over in a more convenient way as negative 1 plus 2 minus sine squared phi. Break that integral up into a sum. which gives you this sum of integrals here. And both of these are, when you simplify the second integrand, both of these are elliptic integrals of two different types. The first one is an elliptic integral of the first type, and the second one is the elliptic integral of the second type. Right. So just like algebraic manipulations, it's really nothing that difficult. And then part C, same thing. They want us to do it for this integral. They want us to write it in terms of an elliptic integral of the second type. They give the hint about the substitution. So again, that's what I did. Part C. All right, so make the substitution. That gives you this integral here. And then using the cofactor identity, sine of pi over 2 minus phi is the same thing as cosine of phi. So the integral here changes into the integral here. Keep in mind your change of limits of integration and the differential as well. You get a negative sign out in front when you make the substitution. And actually the limits of integration swap places. And then you could swap them back by multiplying by another negative, which is where I got that integral from. Okay, and then you can write cosine squared phi as 1 minus sine squared phi, distribute the 4, combine your like terms, you get the integral that I have over here, factor out square root of 5 from both of the terms underneath the radical, and you get this integral, which is exactly what we wanted to do. So you get radical 5 e to the radical 4 over 5 comma pi over 2. Again, e stands for elliptic integral of the second type. Right, and that's it. So yeah, those were the problems for section 1.5. A lot of there's a lot of tedious sort of bookkeeping, I guess, in the problems that you have here, because you have a lot of parameters floating around and so on, and then you may not be familiar with turning an integral into the form of an elliptic integral, but like I said, once you get used to it, it's just another kind of substitution. And the reason that I think he makes you do this here is because this book is kind of old. I think it was written in like the 70s or something, and they didn't really have calculators available to to everybody that would do calculate numerically the value of integrals like we have today. So what they did was they had, if you had an integral like this, you could write it in terms of an elliptic integral, and if the integral could be written in terms of an elliptic integral, you could do that, and then look up the value of the elliptic integral on a table of values, and that would give you the numerical approximation for the integral. It's similar to like, actually, let me just stop the screen share here for a second. I'm actually old enough to remember just barely that math books used to have tables, trig tables and logarithm tables, and they still have tables for example, values of the certain probability distributions, and if you take an elementary probability theory class. But nowadays we have computer technology, where you could the computer will do the approximation for you. You don't really have to look it up in tables anymore. But back in the day, they did have to do that. So I think that's why in this book he made such a big, he makes such a big deal about writing it in terms of an elliptic integral, because you can look the value up on a table of values for elliptic integrals, whereas today, you could just leave it in the form they have it, and a computer will give you a nice approximation right away. So anyway, it's kind of fun to try that. Because it's not something that they show you in Calc 2 anymore, like I said, because we have computers. So all right, so that's section 1.5. Let me know what you guys think. And like I said, the next couple videos will be the finishing my algebra book collection video, and then also I'm going to focus all my attention this week on finishing chapter 4 in Spivak. All right, so you Spivak fans should be happy about that. I'll see you guys in the next video. Until that time, keep learning, and I'll see you in the next one.